clicking a button. Okay, so I should be streaming in about 10 seconds or so. Um, so I did post a video about the solution of the lab from yesterday. Most people got, basically perfect score. A few people did not do step 10. And without step 10, the circuit won't work in my tester. So as a result, those people, do not get points for,
I mean,
the
I
last
don't
part of
know
the
Ryu,
question.
but he might be a good guy. I never played him.
Sorry?
Sorry, I was talking to my brother. Sorry.
Oh, okay. Your mic is on, so all of us can hear you.
Ryu is not a good character.
Still on.
There you go. Alrighty. So what we'll do today is we are going to, well, okay, let me just check my notes here. Um, First thing is prerequisite check. Okay, there we go. So right here, the fourth item from the first module, under course information, is not exactly an assignment. There are only very few things I can do, when I need to, record information. So I made this an assignment. Most of you have 1 out of 1 already, which means I have checked your prerequisite and you're good to go. Only a few people did not have the, or at least I cannot confirm the prerequisite requirement. So for those people, if you see a 0 or a dash with me, anything other than a 1 out of 1, you need to start the prerequisite challenge process. And the way it works, I sent an email already, like last week, is you need to upload a PDF to show me that it is in progress in order to stay in this class. So that means you just need to get a form from the BCS division office, fill it in, okay, make 1 copy for yourself as a PDF, and then post that PDF into this so-called assignment. And I will check that and go like, okay, I understand it is in progress, and I cannot really make it any faster because I cannot evaluate applications for my own classes. So it's going to be somebody else, who's going to have to evaluate it and approve it, or disapprove in some cases. So don't forget to do it if you have not met the prerequisite requirement, or it is marked that I cannot find any evidence that you have met the prerequisite requirements. So that's one thing. I'm just checking my note here. Oh, right. The second thing is how I test the circuits. So there's a link here. I'm looking right here. So there's a link here that kind of describes how I grade the Logisim labs. It's an automated tool, and I made a new script this morning to automatically extract all the files from Canvas, run it through, compare the files, compare the output of your circuit versus what it is supposed to output. So this way, things are a whole lot more streamlined, and so that's why it is kind of important to understand that process. Um, and that was also described in the video that I sent earlier today. So you can go through that video and you can see how I do it. I can explain that when we get to that point too. So that's that. We will have a lab today. Okay, so the lab today is NAND 2. This time I break it up into 2 parts. The first part is the quiz in multiple choice fashion, and that's worth 3 points. And then the file submission is the second part, which is worth 4 points. The reason why I break it up into 2 is partially because it is actually a hassle for me to enter the grade of a file submission type of question inside a quiz. So by making it a separate assignment, it's actually easier on my side. So part of it is for my convenience. And then the other part is, in case people need more time, to create the file and then turn it in, I can now extend the deadline of the second part, but not the first part. The first part is really, I mean, look at this, 3 points, which means there are only 3 questions, 3 multiple choice questions. So I don't think that portion should take too long. The second portion, I don't think it should take too long either. But just in case, right? Um, I'll have the ability to extend one but not the other one. Roll taking, I set a timer already on my watch. So when my watch, goes off, I will tell you guys what the word is. Okay, and that's about it. All the things that I need to go over at the beginning of the class. Are there any questions at this point? All right. I see there are 2 people on YouTube, which is perfectly okay. Just keep in mind that if you're on YouTube, I do not look at the chat channel on YouTube, so you will still have to rely on Discord to communicate with me in text. And the bad thing about YouTube is it lags behind by about 10 seconds or so. So by the time I move on to a new topic, and some people will still be asking questions of a previous topic. All right, so what we'll do is we're going to finish the module that we started on Monday, yesterday, and then we're going to move on to base conversion. So we'll go ahead and start with the module that we looked at the other day. And I'm going to scroll all the way to the almost to the end, and I'm hoping you guys actually got a chance to read the module, because it is really important to review the modules after a lecture, okay? Because the lecture is kind of me interactively trying to talk about the topic, but most of the time, if not all of the time, the material is in written form as well, in more details in the modules. So that's why it's really kind of important to read the modules to make sure that you understand everything and kind of know where to find the details. That's going to be useful when we take exams, when you take the exams. All right, so this part here, okay, section 3.4 talks about something that we already talked about last time, except I did not use this funny symbol, which looks like an up arrow thing, to mean NAND. Okay, so for whatever strange reason, I don't think it's strange. I think the reason why it is an up arrow is because it is kind of like an and. And in logic is kind of looks like a TP or an inverted V. And by putting a stroke through it, it is a negation. So I guess on on one of those really old math specific physical typewriter, my dad had one of those things, so I know. Up arrow is the closest thing that can mean NAND, and that's why it was picked as the symbol for NAND, or negated AND. But we talked about this already. Okay, negation is really just the negation of x is x NAND x. Regular conjunction AND x and y is x NAND y NAND x NAND y. And then regular or disjunction. Now these are the mathematical symbols. Now we don't have to use mathematical symbols in this class. Later on I'll give you guys an idea of what kind of shorthand we can use. But x or y in this case is the negation of x or y. That's just because of the reverse of simplification. We can always add double negation without changing the meaning of an expression. So right here, from here to here, I applied De Morgan's law. We talked about De Morgan's law last time, and I know some people feel De Morgan's law is strange and difficult to understand, but all it really is to say this expression means exactly the same as that expression over there. And as to the proof of De Morgan's law, I remember yesterday I said look at this as a ungraded assignment. So basically you can create a truth table and then figure this out and show to yourself that the two expressions are indeed the same. So I'm going to go over that a little bit today, because I want to show you, what you can do with spreadsheets Yeah, I know, spreadsheets, right? Yeah, but it is actually quite useful. So I'll get to that in just a little bit. And then here we have the negation of x, NAND the negation of y, because this not over here, this not on the outside, is actually applied to this conjunction over here. So we have a negated AND on the outside, so it becomes the negation of x, NAND the negation of y. But through the first rule, we already know, okay, let me scroll up. Through the first rule, we already know how to specify the negation of something using just NAND. So we end up with x NAND x NAND, y NAND y, and that should mean the same thing as a regular OR. All right, so now is a good time to kind of use a spreadsheet to kind of work out these equations. So what I'll do is, there are several ways to do it. I'm going to use a Google Sheet. Okay, so Google Sheets are actually quite useful. The reason why I kind of like Google Sheets is because I don't have to remember to save anything because it is already in the cloud to begin with, and I can very easily share that with the class. So I am searching on the side for a Drive tab. So this way I can create the spreadsheet in one of the folders that you already have access to. All right, so let me. You cannot see what I'm doing right now because I'm doing this in a separate browser that you cannot. I mean, a separate window of the same browser that you cannot see right now. But I will navigate to the shared folder. Okay, now I can put it here. There we go. All right, so everything in the shared folder is already linked at the top part of the Canvas module. So then I'll just go ahead and navigate to maybe examples. So if you navigate to examples as a subfolder of the shared folder, you can see all of these examples. And I'm gonna make a new spreadsheet, and we'll call this. Yes, I can create this in a shared folder, and I'll go ahead and call this. Yeah, the downside of using Google Sheet is sometimes it's kind of slow. So we'll call this OR-NAND, meaning that we are using we're using NAND to implement OR. All right, so I'm gonna I'll do most of this manually, and there's a kind of quicker way to do it. So we'll have true, true, true. Oops. By putting that extra space, it turns it into a string. And then we have false, true, and then we have false, false. Okay, that's a typo. And again, there we go. All right, so column A and column B basically enumerates or lists all the different ways to combine two Boolean variables that are independent to each other. So independent means X is not relying on Y and vice versa, and that's why we end up with 4 different ways to do it. Oh, I can see, you guys are looking at the sheet on your side. That's good. Okay. All right, so now we're gonna use an OR. So OR is easy. Okay, this is the column header, and these are the formulae. Okay, just regular OR, and then we specify the 2 things that we are ORing. And not very surprisingly, true or true is true, and so on, blah 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 blah, like that. Okay, so nothing should be surprising at this point because we all understand what OR is. So at this point, it's kind of up to you. If you want to be fancy, you can go ahead and create your own Google script function, like NAND. So this way you can actually use NAND as a formula. I will show you guys how to do it. So you go to Tools and go to Script Editor, and then you create a function. So give it some time. There we go. Okay, I don't want to call my function. So the simplest way to do it is to just define a new function, and it's called NAND. Give it 2 parameters. And then you just have to return the negation of X and Y. This is in JavaScript, so there's no need for a semicolon, but it doesn't hurt either. So there we go. Now we have a tiny little function here that doesn't seem to be super useful, but I'm gonna have to rename the project just so that it is has a meaningful name. So it's or NAND rename. There we go. Well, it's supposed to have been renamed and not. Nope. Okay, let's do it. It is renamed here. There we go. Okay. So now that we have a function defined in Google Script, I can actually use that function when I need to calculate the NAND of x and x. So I'm going to use the infix notation of x NAND x. So now we can refer to NAND and then refer to x over here and then x again because we are trying to calculate the NAND of x and itself. Oh, okay. And it complains about function not found. Okay, maybe I forgot to save it first. I do that sometimes. Yep, it's not saved because if you focus here, you can actually see there's a little orange bubble. That means the file has been modified but not saved yet. So Control S works here too. So Control S saves the file, and then when I get back to the spreadsheet, it is now available, and takes a little bit of time to do the calculation, I suppose. So I'm just gonna type it here also. Actually, that's a really simple function and it's taking a long time to calculate. Alright, I'm gonna skip over here. This is y NAND y, and then we'll specify NAND of B2 and B2. That is really taking an awful amount of time to update. Finally. Alrighty. Okay, so now we have x NAND x NAND y NAND y. And what that is going to be is the NAND between this value and this value over here. And this time it's faster because I think it might have cached the function. So now I can just extend it to the other 4 rows. Alright, so we are all done here. And you can see how column C and column F are identical on every single row. So that's how we can prove that a regular or disjunction can be done with just NAND operators using this particular way to organize the NANDs. So do we have any questions about the spreadsheet? And by the way, since you have access to the spreadsheet, you can also make a copy to your own drive if you want to. I don't mind you doing it, so that's fine. But do we have any questions? No questions?
Yeah,
Yeah, go
before
ahead.
you went to program that function real quick.
And you mean the Google Sheet, the Google script function like this one?
Yes.
Yeah. Yeah, that's just, it's really close to C syntax. The only difference is you have to spell out, function as a keyword, and the parameters are not typed because Google Script, or basically JavaScript, is not a strongly typed language. But other than that, it does share a good portion of syntax with C and C++. You have access to
And
this too. Yeah, go ahead.
I'm not so sure I understand what you mean by strongly typed. What does that mean in simple terms, if you don't mind me asking?
Oh no, I can explain in hopefully 3 sentences. C, C++, Java are called strongly typed languages because if things are not everything, all the variables, all the values have a specific type. And if they are not compatible, if an operation requires something of a specific type and that the value that you specify is not of that type, then the compiler will give you an error to say that the type is mismatched. In a flexible scripting language like JavaScript, the interpreter would actually look at what is given, the actual value, and the type that is inherent to the value, and they will look at the context of what is needed. And it will try to be smart and go like, I think I can convert this to this. And it will basically do all the conversion automatically. And there's also no compile process to catch type mismatch issues because everything is determined at runtime. And as a result, JavaScript is not a strongly typed language because it cannot statically check the type compatibility just by statically looking at the code. Does that sort of answer the question?
Absolutely, sir. Thank you.
Yep, sure. And then Joseph is typing on the text channel, so I'm gonna wait a little bit here, but I'll use that time to kind of go back to the module. Alright, so the question is that the difference between a compiled and an interpreted language? So yes, part of it. Because a compiled language typically would also be slightly more efficient in some cases, and in some other cases, like really more efficient, a whole lot more efficient. Because with a compiled language, everything is translated into opcode, and we'll get to opcode, about midway through this session, the 8-week session, not just today's class. But because it's compiled to the opcode, which is natively understood by the processor, so things can go really, really fast after a program is compiled into object code. Interpreted means, it will basically reparse the same statement over and over again. Every single time it goes to one statement, it will have to reparse it and figure out what to do. And as a result, it is not nearly as efficient. And then there are languages that are kind of in between. Java is one of those, because Java as a language is actually compiled and strongly typed. But what it cranks out are bytecode. Okay, so bytecode is quote unquote object code. Okay, it's kind of opcode, but it is intended for a virtual machine. So it does have the interpreted portion because because the bytecode has to be executed or interpreted by the Java virtual machine, the JVM. So it has the advantages of both in a way, but it also has the disadvantages of both in a way too. So Java is kind of an interesting case when it comes to strongly typed versus not strongly typed, interpreted versus compiled, and so on. So I hope that answered Joseph's question. Yeah, I don't want to turn this class into a computer language class, which many of you will have to take as an upper division class after you transfer to a 4-year university. All right, so last section before we transition to a new module is about numbers and values. Okay, so the bottom line is what is a number and versus what is a value. So if you look at the my webcam right now, I'm going to hold up a few fingers. Okay, that's a value. But when I say 4, or when I write down the digit 4, that becomes a number. So what is the difference, right? This versus 4. The difference is this is the quantity. Okay, it is just a quantity. The same quantity can be expressed in many different ways. Okay, I can only tell you what Cantonese, what the Cantonese version is for the same quantity. It is say. Okay, so I'm pretty sure many of you also know other languages, and in your native tongue, this quantity is not 4, right? It has another word for it. That is what a number is. A number is a representation of a value. A number is needed when you need to communicate with someone else, or when you need to write down something to remind yourself. That is what a number is useful for. But there can be any number of representations for a single value. For this value here, there can be many, many different representations. So that really is the key to understand base conversion. Okay, because to some people, base conversion can seem difficult to understand, but only because we are looking at it from maybe it has to do with the perspective. Okay, so I'm going to give you some easy perspective to understand base conversion. So before we move on, let me see if there are any questions. I think someone was typing. I just caught a glimpse of that. I am sharing my screen. Let me double check. Yep, I am still sharing my screen because sometimes Discord can crash and and then I'll be talking, but it has actually crashed. So the class, the entire class, has lost contact with me, and I wouldn't know it. But I'm pretty sure it's still up and running now. And Christopher is typing. Hopefully somebody can confirm that we are still up and running. Okay. We good. Okay. All right. So Christopher, you can try to close Discord. I'm hoping you're using the desktop app. You can close Discord and then start it again and see if that fixes the problem. Thank you. Thank you for all the confirmation. Okay. All right, so this module is technically done. Now, with every single module, there are some interesting things about it. It can be definitions of something. It can be something like this, how we can express OR using NAND. So it might be helpful, if you were to write your own notes, okay, or at least somehow bookmark these definitions. So you might want to keep track of, the important points of each module on the side, using whatever means you want. Okay, some people like to write it down. Some people have a tablet on the side. Some people like to annotate, print everything as PDF and then annotate the PDF. Whatever you do, okay, it doesn't matter. You can even copy and paste the entire document into a Google Doc, and then you can do whatever you want with the Google Doc. So all of those things are okay, permissible. All right, so I'm going to close this window, and then we move on to the next topic. So I'm not going to go over WSL2, at least not for now. Instead, I'm going to go all the way to values, numbers, and bases. Because this one does talk about base conversion. There we go. And it's a little bit long, a little bit boring, and so on and so forth. And we'll start with this, okay? I'm skipping a good portion from the beginning. And I'm skipping to this portion here because this is the first portion that's actually kind of, there are certain things to talk about. So these are all in base 10, okay? So everything is in base 10 unless I specify it is not in base 10. So the first part is kind of, this entire thing looks kind of silly, right? Because, 16.375 is 10 plus 6 plus 0.3 plus 0.07 plus 0.005. I'm really hoping that we don't have a question or any problem understanding this part, because that's something that we really should understand, when we get into computer science to begin with. And then we move on to the second part, with the second line, which basically looks at 10 as 1 times 10 to the power of 1. It looks at 6 as 6 times 10 to the power of 0. It looks at 0.3 as 3 times 10 to the power of -1, and so on. So I think most of you are thinking, yeah, that's pretty obvious. Okay, most high school students can understand this. Well, that's good, because that is what a number really is. Because each digit of a number is specifying the quantity of a power of whatever base we choose to use. We are choosing to use base 10 because guess what? We got 10 fingers. So the 1 here is basically indicating that we have a quantity of 1 of 10 to the power of 1. I'm just going to pick this the digit 7 over here. It is telling us we have 7, which is the quantity of, and then we specify a power of 10. Now the power of 10 doesn't have to be of a positive power, it can be of a negative power as well. So in this case, the 0.07 is specifying that we have 7 of 10 to the power of -2. That is how a number works, okay? And you guys would go like, yeah, we know that. Well, then why do we have a problem with base 2, right? Okay, so before we get to base 2, let me illustrate something that would seem obvious to you, but it may not. But no one may have pointed this out to you. Is that you have understood something that is far more difficult than conversion to base 2, and you use it on a daily basis without knowing that you already know what it takes to convert between bases. So I'm going to pull up mousepad. Okay, these are the leftover stuff from last time, so that's okay. We'll just go ahead and make a separate separator here so that we can focus on stuff that is below the dotted line. So what we'll do is we're going to try to specify how to make change. Okay, so assume that you're trying to apply for a job at McDonald's, and one of the requirement is that you need to know how to make change using the least number of coins and bills. So let's go ahead and specify a quantity, and we'll specify $18.75. Okay. All right. So if I were to ask you, using bills and coins that we usually use, how do we make this change? All of you are going to say, oh, that's easy peasy, okay? We are going to use one $10 bill. We're going to use one $5 bill. Okay, $5 bill. And we're going to need 3 $1 bills. And then we are going to have 3 quarters. Okay. Okay. Yeah, that's the right answer. Okay. Even though we do have $2 bills and we have half dollars, those are not very usual, and let's avoid the use of unusual denomination because that can confuse some people. All right, so if you know how to do this already, then you should know how to do base to base conversion already, because the way we look at this, okay, is okay. So we are still staying with the U.S. currency right now, just using the most common denominations. The smallest one is a penny. A penny is 0.01 of a dollar. The next one up is a nickel, which is 0.05. The next one up is a dime, which is 0.1 of a dollar. The next one up is 0.25, which is a quarter. Not counting a half dollar, the next one up is a dollar bill. Then we have a we're not going to count the $2 bill because it's not very usual. So we have a $5 bill, $10 bill, $20 bill, $50 bill, and so on. And to someone who's foreign, okay, to someone who just entered the United States, this is pretty difficult to learn, okay, because a lot of times you kind of have to think about this and go like, because between a penny and a nickel, the multiplier is a 5x. Between a nickel and a dime, just the terms, okay, is already can be confusing to someone who's new. And then between a dime and a quarter is it's 2.5x. And then now we have a 4x, and then we get back to 5x, and then we get back to 2x, and you would think the next one is a 2.5x. No, the next one is a 2x. Then we have the 2.5x. So you can see there's no regularity to the multiplier between the most common denominations, right? So what if I were to suggest that instead of doing something like this, we'll start with an eighth of a dollar. Okay, so 0.125 is an eighth of a dollar. Then we move on to a quarter. Then we move on to a half. Then we move on to a $1 bill, $2 bill, $4 bill, $8 bill. Oops, typo. $8 bill, $16 bill, $32 bill, and so on. What if I were to suggest that we change the currency into all powers of 2? So now how do we make change for the same amount? Okay, so let's take a look. $18.75. All right, where do we start? Come on, you guys can help out here. We start with
16.
16. Yep, so we have a $16 bill, and with a $16 bill, we have $2.75 $2.75 left. Then what is the next?
We could add a $2 bill onto it.
Yep, so a $2 bill. All right, so and then now we have 3/4 left. Then what do we do?
We could add a $1 and a quarter.
We are gonna have a one
We can add a
half dollar bill,
3/4.
and then a $1/2 coin, and then a $1/4 coin. Okay, so somebody type, Jonathan type
Can we do 3/4?
no, because we're supposed to use the least number of coins and bills. Let me explain that after I type this. Okay, so let's just say that you're working at McDonald's and the change is supposed to be $18.75. What do you think is going to happen if you give the customer 1,875 pennies?
Probably wonder where you go then.
Yeah, you probably would get fired, but right before you get fired, I think the manager will look kind of amused. Then the manager is going to say, as amusing as it is, you're fired. So that is why we don't want to use 3/4, because we want to use the least number of bills and coins, okay? And ladies and gentlemen, we have just performed base conversion. And you look at this, okay? You look at this part here and go like, no, that doesn't look like base conversion. Well, let me make it look more obvious, okay? Because we have zeroed $8 bills, right? And then we have 0 $4 bills. So I'm backfilling everything that is absent. We do not have $1 bills, okay? 0x $1 bill. And we do not have any $8 bills as well. So we have 0 times 1/8 of a dollar. Okay, and I just want to be consistent and just add a $sign for each one. Okay, so $sign over here. And now I'm going to use some extra spacing so that we can see the quantity of each denomination. Okay. All right. So the next thing we do is we look at this and go like, how do we express 16? Oh, I know. 16 is 2 to the power of 4. What about 8? It's 2 to the power of 3. Okay. What about 4? 2 to the power of 2. I'm hoping you guys are seeing the pattern now. What about 2 itself? It is 2 to the power of 1. What about 1? It's 2 to the power of 0. What about a half? It is 2 to the power of -1, and a quarter is 2 to the power of -2, and finally an eighth is we don't have any one of those, but it's 2 to the power of -3. Oh, okay, so are you telling me that now we have the quantity of each power of 2? Yes. Isn't that known as a number? Because we looked at a number in base 10 before, and we broke it down, digit by digit, and basically every digit is telling us the quantity of a power of 10. And now we have powers of 2. Oh, okay. So if we just extract the zeros and ones, whether we have or does not have a particular denomination, then we have kind of a number here, right? So we got a 1, we got a 0, we got another 1, we got another 1, we got another 0. Cool. That sort of looks like a binary number. But if I specify this pattern, it's going to be an integer. Okay, my other professor told me that this specifies some kind of integer as a value. Well, that's because we need to separate the power 2 to the power of 0 from 2 to the power of -1 with a point. That is the purpose of the decimal point. Okay, the decimal point is here so that we can know where is the digit corresponding to 10 or whatever base to the power of 0. So if we are to put a binary point, it would have been here. And now we have a binary number in base 2. So when I use parentheses to, after a particular number, it is emphasizing that it is a base 2 number. Okay, so does that mean 18.75 as a quantity can also be specified as 10010.110 in base 2? Absolutely. That is base conversion. Alright, so I'm going to pause a little bit and see if anyone have questions here. We got a few people typing. That's good. How did I get 0.1? Because we have 1/2. The point is separating the quantity of 2 to the power of 0 from 2 to the power of -1. It serves exactly the same purpose as in base 10, separating, indicating where is the digit, indicating the quantity of whatever base to the power of 0.
So just to clarify, you can write any integer as in this form, in this binary form, correct?
Yes.
Like you've written it here.
Yep. Except, certain values may take an infinite number of digits after the decimal point or to the right-hand side of the decimal point. It's just like 1/3. If you want to use base 10 to represent 1/3, the 3 is going to be repeating. So it's the same deal with base 2. Certain values, a lot of values, are going to have a repeating pattern. But other than that, yes. Other than that, yes. All right. So let's go ahead and I'm just looking at the time. Okay, we got plenty of time. So let's go ahead and do some base conversion, but using some really oddball base. Okay, so now we want to convert to base 7. Okay, and you guys would go like, base 7, that is really strange. Who would use base 7? Well, I'm gonna I'll show you 2 examples. Okay, one would be the aliens of was it Arrival, the movie, the sci-fi? So okay, let me see if I can do this on the chat channel. Yep. There we go. So the aliens in the movie Arrival, have 7 limbs instead of 8 as in octopus. So they're also called, is it hexapod? They're hexapods because hexa means, no, hepta, H-E-P, heptapod, which means 7. But at the same time, octopi who likes to drink would also use base 7 because they need one tentacle to hold on to the beer. Okay, you guys are not getting it. There are a few things kind of not illogical about this, because how do you drink beer underwater? That question can be answered by SpongeBob, right? And then the second question is, why would octopi drink beer? I'm not even sure beer would affect octopi because they have an entirely different blood chemistry compared to us. So, but anyway, we're just gonna use that as an excuse to play with base 7. So we'll start with something that looks very nice to us, like 200. Okay, so if I want to convert 200 in base 10 into base 7, oh man, how do we do this, right? So we always start with the higher powers, and then we work ourselves to the lower powers. So the question really boils down to, do we have any 7 to the power of 3? Do we have any 7 to the power 7 to the power of 2. Do we have any 7 to the power of 1? And do we have any, okay, plus, do we have any 7 to the power of 0? So we have to somehow answer all of these question marks. So it would be helpful if we know, the powers of 7 in base 10, right? So 7 to the power of 0 is 1. That one's easy. 7 to the power of 1 is 7. That's easy too. 7 to the power of 2 is 49. Yeah, I think most of you know that. And then 7 to the power of 3, or 7 cubed, is 49 times 7, which is 350 minus 7, right? So it's 242. Whoops, 343. There we go. I think that is right. Let me just double check. Because it's 49 times 7, and 9 times 7 is 63. The 6 goes to the 28. So we have 34. So that is correct. Okay, there we go. All right, so first question first. Start with a higher power. Do we have any 7 to the power of 3? The answer is no, because 200 as a value is less than 7 to the power of 3. So we do not have 7. We do not have any 7 cubed. Then the next question is, do we have any 49s, basically? The answer is yes, we have a few. Okay, so this is where base conversion other than base 2 kind of comes in, and is kind of ickish, because we need division. Okay, with base 2 we don't need division. All we need is compare. Okay, greater than or equal to or not. Okay, that's all we need to know when it comes to base 2 conversion. But with all the other bases, we actually have to do division. So now we have to divide 200 by 49, which is pretty easy because 49 is really close to 50, and we know there are 4 of those. So we'll say 4. All right, so we have 3 as a remainder, and that means we don't have any 7s. And then we have 7 to the power of 0 left. So that means we can now rewrite this. Okay, remember, a number are basically digits indicating the quantity of each power of whatever base we choose to use. And because we are choosing to use base 7, so now we just need to indicate the quantity of each power of 7 in order to add up to the quantity of 200. So we have a 0, and then a 4, and then a 0, and then a 3. And to emphasize this is in base 7, we just have to say it's base 7. That's all. Do we have any questions?
Yeah,
I
how do you
might have
know
made
how
a
high to
mistake.
start your bases from?
Huh?
Because you're starting it from the power of 3, but what's to say it couldn't have started from the power of 4 and only gone to the power of 1? Or why couldn't you start from the power of 1 and go to the power of 3? Like, what I'm saying is, how do you determine if it's starting from a really high base or a really low base from the left-hand side, or am I just mistaken?
You're always going to start from the higher powers because we want to use the least number of bills and coins. So you always want to start with whatever power that is high enough to cover the value that we are trying to deal with. Because we don't want these quantities, we don't want any one of these quantities to exceed or even to match the base itself. So none of these digits should be 7. They all should be 0 to 6. It's just like in base 10. Okay, if you think about a base 10 number and look at every single digit of a base 10 number, they only go from 0 to 9. The quantity of 10 does not have a single digit to represent it. And it's the same thing when we convert to other bases. The digits can only go from 0 to 1 to whatever base minus 1. Is that making any sense?
I mean, I think it's just a little unfamiliarity with it. I think
Okay.
it'll be clarified at that time.
Okay. All right. Um. Okay. So let me see if I can use this as an example. So I'm going to use a bunch of pound signs to express the quantity that I want to represent. Okay. And I really don't know how many there are, but I'm going to ask you in base 10, how do I specify the number of pounds that we have here? Where do you start?
From left to right, counting one by one.
So you can count one by one, but you can also do something like this. You can basically specify this is 10 to the power of 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10 to the power of 1. And then when you have 10 of these, then you have 10 to the power of 2, which is 100, known to us as 100. So you're going to have to, okay, so I'm going to actually do it here. I know it sounds kind of unnecessary. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. So now you look at the quantity that we want to represent, which is this thing here. And we want to specify how much of this, how much of this, and also how much of this do we need to make up the quantity, which is only this much. So we need to make sure that whatever base we start, whatever power of 10 we start with has to be at least as long as the quantity that we want to represent. Does that make sense? So in this case, we would have no hundreds, a few tens, and then maybe a few ones. Not sure whether that's making sense or not.
Okay. All right.
Okay, all right. Okay, cool. All right, so, but there are equations, there are formula that we can use here. So going back to the notes, and I'm hoping that some of you, or I'm actually hoping all of you had a chance to read this, but I know that is not the case. So the way we represent a value, which is represented by the letter V over here, is basically a digit. This is all in base 10. Okay, so in the case of a base 10 number, D0 is representing the digit corresponding to 10 to the power of 0. D1 is corresponding to the digit for 10 to the power of 1. D negative 1 is corresponding to the digit that represents the quantity of 10 to the power of negative 1. So it really is just a summation. And the way to kind of make this a little bit easier to read is to use the sigma notation, which is the summation, notation. And the index I'm going to use is just going from negative infinity to positive infinity, because there's technically no limit of how many digits we can use to represent a value, because we can always use a whole bunch of leading zeros to the left hand side and a whole bunch of trailing zeros to the right hand side, because both ends can extend to no end, and you're still maintaining the value being represented. So that's why I as an index is starting from negative infinity and it's going to positive infinity. But each term that we're adding is di, which is designating a particular digit in the base 10 number in this case, times 10 to the power of I. So the really important part here is the I has to match. In other words, the digit has to match whatever power of 10 that we are dealing with for that particular number. So this is good for base 10. What about other bases, right? So to extend this argument for other bases, we just replace 10 with whatever base b that we are using. So if we're using a binary number, b becomes 2. If we're using base 7, b becomes 7. If we're using base 16, b becomes 16. So do we have any questions about these notations, especially the sigma notation, or what d of I is representing? Okay, I'm not seeing or hearing any questions.
What is d of I representing?
It is explained here in the paragraph. So given that a number has di as the ith digit, it's digit I. All right, so I think a tablet, using my tablet may be better here. Let me start up my screen for the tablet. All right, and I'm gonna make it fit. All right, so we're gonna use the number that we used earlier, okay, which is 18.375, and it's in base 10, okay? Oh, you guys are not, it's not actually doing it. Okay, let me get rid of this and then start it up again. Yeah, sometimes the program doesn't start correctly the first time, but I'm gonna try again. There we go. It is called Remarkable. It's actually a physical tablet, but I have an app, that mirrors the screen on the tablet over. I can show you the tablet. Just give me a second. Let me make sure the USB cable is long enough. So this is the tablet. It's black and white. It uses e-ink, and it is called Remarkable. So Remarkable is the name of the tablet. I mean, you can use an iPad, for the same purpose, but I just find this device to be better for me because it's very distraction free. It cannot do email, it cannot do text, it cannot do a whole bunch of other stuff. All it can do is write and read PDF. So it's kind of useful that way. Okay, so with this thing, okay, now it's working. So with this thing here, this is actually D0 because it is the quantity of 10 to the power of 0. This one here is D -1, D -2, D -3, and then this is D1 because it is representing the number or the quantity of 10 to the power of 1. So does that answer the question? I will take that as a yes. Okay, all right. So moving on. Okay, 4 more minutes before I take roll for today. All right, so to convert a number, there's an easy way to do it. So the easy way to do it, skipping everything, all the discussions, all the way to the equation. So d of I, which is only one digit of the number in base b. So d of I can be done this way, and this little symbol here means the floor of something. Okay, so the floor for the most part is kind of like rounding down, okay, taking the integer portion of something. So as long as v is not negative, we are fine. Okay, when it's negative, then the floor is kind of not really applicable. But since we assume that v is not negative, we can just say we are taking the integer portion of a division. That's what the floor symbol is representing. So we divide the value by b to the power of I, and then we mod it with b. Okay. So let's check out whether this works out or not. Okay, I'm just going to write this down on the side. Okay, and we'll see whether it works for the examples that we have worked out already. Okay, so I'm going to switch back to the tablet. Okay, we have the equation. First of all, we'll check our base 10 representation. In fact, we are going to check this number here. Okay, see if it makes sense, see if it works. Because if it doesn't work with this example, we have a problem. So now we say, what if I equals to 0? Then we have D0 equaling to the value, which is 18.375, divided by 10 to the power of 0. Take the floor of that, and then we mod it with 10. What is that? It becomes 1.8375. Take the floor of that, mod that with 10. And what is that? That is... Oh, I take it back. Sorry, I messed up here. It is 18.375 because 10 to the power 0 is 1. Duh. Okay, so we take the floor of this, and it becomes 18 mod 10. And 18 mod 10 is 8. So D0 is supposed to be 8. And guess what? We got that. Cool. You guys are going to go like, yeah, looks like this is circular reasoning because you started off with a base 10 number to begin with. Well, that is actually not the case. Okay, this is really just specifying a value. Okay, the value is, I use base 10 because we are used to using base 10 to specify values. That's why it looks like a base 10 number. But all it does in this case is it specifies a value that we're trying to convert into a number in base 10. Okay, but Tech, you worked out an example earlier. Why don't we use that one to check? So let me go back to this one here, okay? And we're gonna go check out, okay, which digit do we want? Maybe this one here. This one looks fun because it is a negative power of 2. Okay, so I'm gonna jot down, this is D negative 2, B is 2. Okay, I'm just jotting down on my tablet, and now we can switch back to the tablet. Okay, so this time we're looking at D negative 2, which is the quantity of whatever base, which is 2, to the power of negative 2. So now we say D negative 2 is the floor of 18.375 divided by 2 to the power of negative 2, and then the whole thing mod 2. Alright, so hold that thought, okay, because my timer just went off. I'm going to take row right now and switch to, you cannot see it yet, okay, so until I say refresh your screen, you won't be able to see it just yet. This is the 2021-06-08 row taking activity, and let me let you see the answer to the question, because all you need is to type that in and you're all good to go. Alright, so I have chosen the word arrival, all lowercase, no exclamation point, just the word arrival in lowercase as the word for taking row today. And I'm going to specify the time frame of taking roll. Alright, so it's June 8th. Oops. June 8th. And the time right now is 1832. So it's 6. I'll give you guys until... I'll give you until 6:40 p.m. Okay? I don't think anyone is going to take that long to answer this question, but that's okay. Alright. Save and publish. And I'm going to write it down in the text channel as well. Oh, okay. Got it. Thank you, Paul. I'll address that later. But I will also make sure that everybody know what the row taking word is in the text channel. So go ahead and do it. I'll give you guys like maybe a minute to do it, and then we'll get back to the base conversion thing that we were talking about. And by the way, if you have not watched Arrival, I think it's a pretty cool movie.
That was the movie that you posted a GIF of in chat, right?
Say that one more time.
That was the movie that you posted a GIF of in the chat, right?
Yep. I mean, the whole premise is also kind of interesting. Why the aliens came to Earth. Alrighty. So I think most people have done this already, and I am going to move on to this calculation here. And as Paul, kindly, noted, I made a mistake because it's not supposed to be 375. It is just 75. So I'm gonna make a change now. Okay. All right.
Also,
Go ahead.
I have a question. You said when you were doing the calculation off to the right-hand side, taking the floor of the equation. What does that mean?
So the floor of x is the largest integer that is less than or equal to x. That's basically what it is. So when you take the floor of 0.5, what is the largest integer that is less than or equal to 0.5? That would be 0, right? So when x is negative, it gets a little bit tricky because if you are looking at the floor of negative 2.1, then you have to answer the question of what is the largest integer that is less than or equal to negative 2.1. And the answer is not negative 2 because negative 2 is actually larger than negative 2.1. So the answer is negative 3 in this case. So that's basically what floor is, what floor does. But assuming the value inside the floor operator is non-negative, then it's really just the same thing as truncating, getting rid of the fractional part. All right. So any other questions before I get back to this calculation? No questions? All right, so let's go ahead and do this calculation. So now we have 18.75 basically divided by 2 to the power of negative 2 is 0.25. And then take the floor of that, and then we want to mod 2 after the floor operation. So now we have to answer the question of how many quarters do we have in 18.75. I'm going to do the math on the side here. So we have basically 18 times 4, which is 72, plus 3, so that's 75. Okay, so it's the floor of 75 mod 2, but 75 is the same. The floor of 75 is just 75, so it's 75 mod 2, and it is 1. And I believe the conversion that we did earlier also has the digit for position negative 2 being a 1. Okay, so let me point out where we are talking about here. We're talking about this guy here. So we are getting the 1 back. I mean, by no way is this a proof of this whole thing actually does work, but it's a good confirmation. By applying it, now we actually get to see how this works. Any questions? No questions. All right. All right, so if there are no questions, we're going to move on. We are pretty close to being done here. So how do we deal with base 2 numbers? We just say b is 2. B is a variable, that is corresponding to the base, of what we're converting into. So that's, that's pretty easy. Now, the equation that I give here will only give you a single digit at position I. So it's not going to give you the entire number, but by iterating I through different values, you can get to all the digits of a number. Do we have any questions over here? Okay. So the question now is, why is base 2 particularly important in computer science? Kind of gets back to what we talked about yesterday. So I'll let you guys kind of think about this a little bit. Why do we care about base 2 more so than, say, base 7? Okay, why is it easier for computing? Two states. Yes, exactly. Because everything has two states in a digital computer. So when we say digital, okay, because we say, oh, digital art, right? Digital da da da, digital da da da. Technically speaking, it can be even more specific because it's actually binary, okay? Because inside a modern computer, things are not only digital, they are actually binary. They're all represented by um, internally it's not zeros and ones. Okay, remember, we are interpreting voltages. Okay, a voltage that is above a certain threshold is interpreted as a 1, and a voltage that is below a certain threshold is interpreted as a 0. So 0 and 1 is not even native to the physical states. Zeros and ones are already interpretations of a physical state. But that's how we do it. Okay, we basically just everything is a 0 or a 1. A very good example of binary is not even the logic gates that we talked about, Joshua. I mean, um, Queen, Hawkeen, Hawkeen. Okay, if I mispronounce your name, you can correct me. So the important part is everything that we do with computers are either zeros and ones, because if you look into a CD, okay, a compact disc, if you are relatively young, you will have to ask your parents of what a CD is. Okay, a CD is a compact disc, and it's basically just walking. Okay, hawking, hawking. Okay, so walking. Okay, um, so it's the presence or the absence of holes on a reflective medium, and that's how we used to encode music. So once again, boiling down to zeros and ones. And somebody's going to ask, but why are we only representing things using, the absence or the presence of something? Can't we use a larger hole, smaller holes, and so on to encode more analog information onto a medium? Well, the answer is yes. But if you start to do that, then the margin of error becomes a problem. Because, how big, what is the threshold of registering a hole as a 1 and then registering as a 2 and then registering as a 3 and then registering as a 4? So now we have a margin of error kind of issue, and that becomes sort of a problem, okay? If it is only zeros and ones, well, that's pretty easy. We have a pretty large error of margin before things start to go wrong, okay, and which is good, okay, because in a binary digital computer, we can have all kinds of noise being present, and it doesn't really quite affect the processing of information. So that's good. But there's one more thing that is actually kind of neat about binary numbers, because we can look at 1 as true, we can also look at 0 as false. Okay, so that's just a different way of labeling the physical quantities. What difference does it make? As it turns out, when we want to add numbers, okay, which is an arithmetic operation instead of a logical operation, as it turns out, there are ways to translate arithmetic operations in base 2 into logical operations dealing with Boolean values. Let me say that one more time, okay? Because some people may not have caught what I just said. What I said was there are ways to convert arithmetic operations in base 2 into logical operations in Boolean. That is cool because it means now we have a way to utilize the gates that we have talked about, the NAND gate to start with, and then once we have the NAND gate, we can implement the negation gate, the conjunction gate, and also the disjunction gate. So we can now translate arithmetic operations like addition, subtraction, and with those we can then translate multiplication and division. So now we can do everything using logic gates, because now we can, and logic gates can be implemented with transistors. Okay, so that is why binary numbers are really cool, because now we have a way to utilize transistors to perform all the operations that we want a processor to perform. Okay, so that's why base 2 is particularly interesting to computer science people, because it makes it possible to create machines that can do the calculations. So now we are at the end of this particular module. This one talks about how values are represented. Everything is actually in base 2 internally, even when we see things that are in base 10. So that base 10 pretends is actually just being there. Section 8 talks about basically you can look at this as another ungraded assignment, is writing a program to do base conversion. So you can start with an arbitrary base, let's say in base 7, and then you print the value of that number in base 10. Or you can go the other way, you can specify a base 10 number and then convert it into an arbitrary base, like base 2, base 7, base 5, base whatever, okay? So I would say, do this on your side. I'm not going to grade it, but if you just kind of examine how to write the code in any language to do the base conversion, and particularly base conversion that are not native to a programming language, because in C and C++, base 16 is native, base 8 I believe is native, base 10 is also native. Okay, so conversion to those bases is pretty easy. But if you try to convert to base 9 or base 7 or base 3, those are very odd bases that are not supported by the programming language itself, nor its libraries. Then you have to actually write code and think about how to do the base conversion. And there are many different ways to do it. Okay, you can use an array to do it. Okay, step by step. You can also use a recursive algorithm to do it. Okay, so there are tons of different ways to do it. I would do this as an ungraded assignment, which means I'm not going to grade it, but I think it's going to be beneficial if you do this. You would start to have a better understanding of base conversion. So that's what section 8 is. And we're done with this module. Okay, so we're done with an entire module. And now we can go back to all the different modules so I can show you what we'll be talking about tomorrow. And we are really just moving down, one module at a time, one section at a time. So the next one is going to be binary number addition. Okay, so this is it's a deceptively difficult module to understand. So I would definitely, spend some time to pre-read before the lecture and then jot down any questions that you might have, so that in class when we get to where your questions are, you can start to ask the questions in the text channel. So that is highly recommended. And at this point, I'm going to release today's lab, which is NAND2 and also NAND2 file submission. So let me go here. One has a passcode that you need to enter first. So I think it is the first one, which is the lab. And the passcode is Nandroid, if I remember right. Yep, so it's Nandroid. It's kind of like Android with an extra N at the beginning, all lowercase. So that's the passcode, and we'll make it due at the end of the lab session. This one is not nearly as long as the one yesterday, or I hope it's not. So I'll make it due at 8:20 p.m. and now it is published. And I'm going to release the companion assignment, which is really just collecting the circuit file that you create out of this one. And we'll make it due the same time, because it used to be the same lab. Okay, it used to be a part of the lab, but for grading purposes, if I separate it out as an assignment, it's easier for me to collect and grade it. So we'll make it due the same time, which is June 8th. Oops, June 8th, 8:20 p.m. June 8th, 8:20 20 p.m. There we go. All right, so the lab is released, and we are almost right on time for today's lecture. Cool. All right, so any questions? The laser eyes, like Superman.
I have a question.
Mm-hmm.
Regarding your office hours, are we allowed to get into voice calls with you, camera calls and the like, or is it just messaging through Discord?
All of the above. So, I'll be, if I remember right, it's from 11 to 12. Okay, let me double check. It's in the syllabus. So if you click on the professor section, oh, I did not specify that. Huh. Okay, well, then I need to go back and re-specify that. So the office hour is from 11 a.m. to noontime. But it can be done over Discord. It can be done over direct messaging. It can be done on the general text channel, email. Just about any medium is fine. The wait list has not moved since yesterday because no one on roster is absent, so I cannot. There's no reason for me to drop anyone from the roster, so I cannot move anyone from waitlist into the roster of the class. I would wait, at least keep attending the classes until Thursday, because people who do not meet the prerequisite requirement and do not indicate that an application is in progress by Thursday, those people will be dropped. So potentially we might have openings on Thursday. Also, people who have missed classes for 3 days will also be dropped. So if people miss today, Wednesday, tomorrow, and also Thursday, those people would also be dropped. So there's also a chance of some people being dropped on Thursday. All right, so we have for graded programming exercises later. Those will be in C, C++. And okay, so this is really cool. If you don't have an environment to write C programs, there's a site that you can use. It's called Online GDB. So Online GDB, just like the name, onlinegdb.com, is a place where through a web interface, you can create your C, C++, along with many other languages. So if you click on the language, you can handle Java. It can handle. Does it handle Node? Has Perl. So Perl is kind of cool. Assembly, don't even try. Okay, that's not the assembly language that we're gonna use in this class, so it's not gonna be very useful for us. But definitely C and C++. And you can run the program. It has GDB built into it, so we can also debug programs using this web interface. So it's really cool. That's what we're gonna do when it comes to time to program in C and C++. Yeah, I think it's pretty cool as a resource, because now you can use a Chromebook and still be able to write and debug programs. So there you go. All right, so I'm not seeing any additional questions. So I'm gonna get off of the voice channel and stop screen sharing. And then I'm gonna go off, get something to eat, and then we'll come back in about 10 minutes. So the time is 6:55 right now, so I'll be back at 7:05. And I'll also add my office hour to the syllabus, and it is from 11 a.m. to 12 p.m. to noon. So that's my office hour. So I'm going to write it down here. 11 a.m. to 12 p.m. is my office hour. So via Discord is preferred, but if you want to use other channels, that's going to be fine too. All right, so I'm going to get off of screen share. And off of the voice